Hello everyone, and welcome to the second video in our Class 10 time series of lecture videos. In our first video, we ended after discussing a few more definitions. All molecules that have non-superimposable mirror images are chiral. Chiral molecules and objects are non-superimposable. And if mirror images are superimposable, then the molecules or objects are achiral. Which means they're identical. So then we took the example of 2-methylbutane and we asked, is it chiral or not? And even though it looks like its mirror image is non-superimposable, there is a way you could rotate around carbon-carbon single bonds to make all of the groups and atoms in this reflected mirror image of 2-methylbutane superimpose on the original image. And so we decided that this was achiral. It's kind of difficult to do that for all types of molecules you encounter. So we asked the question, how do you tell if a molecule is chiral without looking at all the possible conformations? Well, here are a few rules that can help you with a good number of examples you might run into. 1. If a molecule has one and only one atom with 4 different groups attached to it, it will always be chiral. So that means it will always have a non-superimposable mirror image that is defined as its enantiomer. Number 2. For most organic molecules, only one test is necessary to determine if a molecule is chiral. If a molecule lacks a plane of symmetry, that is an internal mirror plane, then it is chiral. Wow, that's a pretty big rule, and it's going to be tough to wrap our minds around it. It follows from rule 2 that if a molecule possesses an internal plane of symmetry, that is an internal mirror plane, then it will be achiral. So why don't we test this idea out with 2-methylbutane. So I built a model of 2-methylbutane because I think it would be easier for students to see that model. I think in our lecture notes we had the methyl group pointing up out of the plane of the page at us, and we said, oh, its reflected mirror image is actually superimposable with it, so it's achiral, which means it must have an internal plane of symmetry. Well, where is its internal plane of symmetry? It's kind of difficult to see in this conformation. However, if I rotate a little bit around this carbon-carbon bond, and then I turn the molecule this way, wow. Does everybody see a plane of symmetry that cuts right down the middle of the molecule? So it slices it right in half vertically in this, photographed image. These 2 methyl groups reflect into each other, so those 2 methyl groups reflect into each other. These 2 hydrogens reflect into each other. These 2 hydrogens in front reflect into each other. And the thing with an internal mirror plane is it cuts this hydrogen in half, so half that hydrogen reflects into the other half of the hydrogen, and it cuts this carbon, this carbon, this carbon, and this hydrogen atom in half. And so those halves, in theory, reflect right into each other. So that's what we mean by an internal plane of symmetry, an internal mirror plane. And so because 2-methylbutane has an internal plane of symmetry, well, we know it's achiral. So that's a kind of neat test that you can apply as you look at molecules. So let's look at some other examples because, I don't know about you, but I grew up in the University of Hard Knocks, and I learned by examples. So, if there's a plane of symmetry, the molecule is achiral, like we discussed. How about dichloromethane? There's a lovely molecule, right? Accused of being carcinogenic. I probably would not like to breathe a lot of it for fear of liver damage and oxidizing it up to phosgene. Not a good thing. So this molecule has a mirror plane in the plane of the page. So it's achiral. And you only need to find one. For dichloromethane, we actually have two mirror planes. So here's our dichloromethane. There's one mirror plane that's vertical. And here I've oriented it in another orientation. And again, you should be able to see that there is a second vertical mirror plane. So there are actually two mirror planes for dichloromethane. Neat, right? How about 2-butanone? Is this chiral or not? So there is actually a mirror plane in the plane of the page. So it possesses a mirror plane, and that means this molecule, this 2-butanone, is achiral. So always be mindful of free rotation, and of course practice is important. It's good to practice with those recommended practice problems and exercises in your text. How do we name enantiomers? And this gets to an interesting question. Well, first we need to assign absolute stereocenters. So there can be two types of stereocenters. You can either have an R designation for your stereocenter, that's an atom that has 4 different things, or you could have an S designation. So how do we make those, assign those designations? Well, what you have to be able to do is assign priorities for the different groups coming off of your atom that has 4 different things attached to it. That's your stereocenter atom. So let's take this, theoretical carbon atom that's a stereocenter, and it has 4 different groups hanging off of it. You have to prioritize those groups. So let's say one of these groups is the highest priority. We'll label that number 1. There's the second highest priority, 2, third highest priority, 3. The lowest priority substituent we label 4. So to technically determine whether that stereocenter is R or S, what you need to do is pick this tetrahedron up and, like a tack, pretend that 4 is sharp, tack it into the wall or the plane of the page. So you put 4 in back behind the plane of the page, and then you connect your priority 1 to priority 2 to priority 3 substituents. And in the process of connecting them, you'll see that we are going in a clockwise motion. So if you go in a clockwise motion from highest priority to second highest to third highest priority, that is an R stereocenter. Here we've drawn the mirror image of our starting stereocenter molecule that we're using as a demonstration. So 1, 2, 3, and 4 priority groups. Again, we put 4 back through the plane of the page, and then we connect 1 to 2 to 3, and now we see that we are going counterclockwise. That will be an S designated stereocenter. So now we know how to assign stereocenters for molecules that may be chiral. So we will practice some more in our next video, and I look forward to teaching you guys a little bit more about stereochemistry there.